Great, so now let's look at this example from 3.7 in the prescribed textbook. What we're going to do is, first, before we start solving with two 3-noded elements, so instead of doing that, we're first going to solve it with a single 3-node element. Okay, just to make sure we're comfortable with it. But what I'm going to do is, I'm going to solve it properly. And what I mean with that is, I'm going to solve the linearly varying body force as linearly varying. I'm not going to assume it to be constant over the element. Okay. So, and I'm going to do it with a consistent node load. So what the textbook does is it does compute the consistent node loads, but it assumes that the linear varying body force is constant over each element segment. And that is a overly simplified way of solving the problem. In this course, when we have linear varying body forces, we solve it as linearly varying and compute the consistent nodes for that linear varying body force, unless it's explicitly stated that we make a simplification. Okay. So that is important to highlight that clearly. So in the example of the textbook is there's angular velocity is 30 radians per second, and what we see is we can do a couple of computations. So what is the weight density? So the weight density is really just the weight, which is mg divided by the volume, so it's Newton per meter cubed. The centrifugal force is essentially meter omega squared x, so that is the force due to the fact that the thing is spinning around, and that is where the linear varying body force comes in. So it varies linearly from the center towards the outside. Okay, so that is important to understand, and that is that we can rewrite a little bit by saying this mass we can write in terms of isolated mass here, and then write it as rho over g times the volume times omega squared over x. So that's really another way of writing this centrifugal force. And if I want to write this not as a force but as a body force, then I just divide by the volume, and then I end up with this expression here. Okay, so that's what we have. Okay, so this allows us to now compute this centrifugal force and the centrifugal body force, okay, over the element. The exact stress solution, I'm giving it to you here so that you can see what the exact stress solution looks like for this problem, and we're going to compare against that. Okay, so that is the same solution that they plotted in the prescribed textbook. Okay, and then the work done by the body force is equal to the strain energy integrated over the volume. That's what we have. Okay, so let's start solving this problem, and let's see what's involved. So we're all comfortable with this single element. This is what we're going to do. So first off, I'm putting down my shape functions n1 to n3. I'm doing a mesh, and I'm choosing where I put the nodes. I said x1 at 0, I put x2 at 42, and x3 at 21. So that is a nice numbering that we're used to. And I can do my isoperimetric formulation. Okay, so remember that in x3 is the mid-side node. This is the right-hand side, this is the left-hand side node. If you think of x at the left, x equals to 0 at the left, and x equals to 42 at the right. If you visualize it like that in your head. And then we have essentially an area, which is a constant, but again, I add a 0 times xi to make sure it's the right type. The object type is the right. Okay. Then I'm adding in all this information just from the problem. This is what we have stated, given by the problem. The Young's modulus, PSI, the G in terms of feet per second squared, etc. So this is just given information, and here I can compute essentially the associated body force, okay, that we have acting over that structure. Okay, what is this body force? Why is this here? What does it say? Traction. Okay, set a list of so just I don't know why this is essentially our body force that we have, the non-zero body force. List of shape functions n1 to n3. There's the shape functions, and then we can now compute the properties like we've usually done, dx dt and dt dx, and then we can compute the P matrix as derived by array for n with respect to psi multiplied by dt dx. So this is now spatial with respect to x. Okay, again, so this is what we have. Okay. Here I just expanded it a bit by saying if you want to leave the multiplication symbol to do linear algebra, you can cast B into a column vector and then use SymPy matrix to do that. Okay, so that is if you would like to go that route. So SP matrix, B matrix, the transpose, so that is a column vector, and then if I make so this is a 3×1 vector, and then essentially if I do the transpose, it becomes a 3×1 times E times 1/3. This becomes a 3×3 matrix then, if I do that. So then I can leverage the multiplication symbol if I've made sure that these are SymPy matrices. Okay, my integrand is just given by the B transpose EB times A times the psi, the X d psi. Okay, so that is what we have. So that is our integrand that we want to try and compute. And now we can say, well, there's nothing funny here, so we know that the two-point Gauss rule will integrate this exactly, so we can do that because the area and the Young's modulus are all constants. The body force vector results in force given by this, my integrand for the body force, fxa times the shape function times the x d psi. Again, I can integrate this. If I look at the highest order in the shape function, see I can integrate this with the two-point Gauss rule to be exact. And they have computed down my body force. And take note, fx is something that is a function of, where's fx? It's something that is a function of make sure what is, yeah, it's fx is a function of x, which is in turn a function of psi, like we just discussed there. Okay, so that is essentially what we have. So this is what we have with the integrand. Okay, so now we've computed fx not as a constant, but as a linearly varying thing. Because x is a function of psi, already expressed by the supermetric formulation. That is important to understand. Okay, great. So that sets the scene. Now we can say, after we've integrated, we can reduce the system. We can get all the, eliminate the rows and the columns associated with variables that are known, and that is just the variable q1 or at x equals 0. So we can reduce the the forces as well. And I'm just taking over that 0 times that column of what the 0 we have multiplied to the right hand side to adjust my right hand side. In case this was not 0, in this case it's just 0, so it doesn't matter if you add it in or not, but I'm always adding it in just to make it explicit that you can see matters. Okay, so that is then essentially the reduced stiffness matrix with the reduced force vector, and now we essentially can sort of get a solution out. Now we can go for the solution and see what the time is. Okay, it's still 8 minutes, so I'm going to continue for another 3 or 4 minutes and I'll stop the video to make it not much longer than 10 minutes. Here essentially we have the displacement vector that we set up now. So q1 is 0. This was a prescribed displacement. This is the solution, the two solutions we got, and now I can set up q as the full displacement vector for the solution. Okay, that allows us now to plot the displacement field. Okay, the q is multiplied by the shape functions. That's my field, and I can look at how that displacement field looks. I can compute the strain field by multiplying the B matrix with q, and here I'm using the inbuilt-in dot operator of the B matrix. And then essentially that. Compute the stress. This is the exact stress solution. This is the, and then I can plot sort of the stress and the exact stress over psi from -1 to 1. Okay, and then I can have the internal force as well. That's just the stress times the area, and the exact internal force as the stress times the area, and then see how that looks. Okay, so that is the first thing we can do. Other aspects we can go and compute are related to the work, but before I get there, let's just look at the plots first, so that we just first solidify this for ourselves. So when we start looking at the plots, we see that the displacement looks like this. I have to first ask, does it make sense? So the displacement at psi equals to -1, on the left-hand side with x equals 0, that's 0, that is correct. Essentially, we see that the displacement towards the right-hand side, we can ask ourselves essentially what is the situation there. And we see essentially that the displacement sort of tapers off towards the right-hand side. And we can ask ourselves, does that make sense? Well, first off, the point that is where it's attached experiences the whole body force acting at that the entire loading due to the body forces of that entire structure is being resisted by the edge around which it rotates. So that will see the highest load, and the load will decrease as we go towards the right edge. I mean, the point on the edge of the other side, there's essentially no body force acting on the remaining material onwards, because that's the edge of that bar. And so we expect to see essentially the loadings the highest here. So we see sort of the displacement slope. If you want to relate that to strains, we can see that's the highest here, and it tapers off towards the. So that is what we would expect to see. Again, this is a quadratic function for displacement, so the strain must be linear. So that is what we see. It's just the derivative of this quadratic field is a linear field that we see out here. And essentially I see the strains is the highest at the place where it's rotating, and I see the strains going down. I might have expected to see at that edge, on the right hand edge, that there should be actually 0 strains. So that maybe this thing should have tapered off completely flat there. So that is expectation that one might have. Okay, so then when we look at that, and we start looking at the stress, so this straight line, again, strain is straight, the stress must be a straight line, because the Young's modulus is not, is only a constant. That straight line stress, we can see that at the end of psi equals to 1, that the stress is not 0. Although that is the end of the bar, and there's essentially no additional material pulling on that edge. There's no traction at that edge of the bar. But in case of this solution, we see that there's indeed actually a traction that's acting there. And so this is what the approximation is doing. So at that right-hand edge, where at the edge of that bar, if you were to put a dot stress sensor with a normal upward pointing but you would expect to see 0 traction. There's no traction applied there, and there's no body forces that's beyond that, that's pulling on that part of the material. But what we see is that there's indeed in the approximation there is a non-zero stress at that edge. And so what we see is the exact stress solution looks something like this. So what we see is we overpredict the maximum stress in this case, and we sort of let's call it also, I mean, depending which one says, our lowest stress is not as low as what we would have expected. Okay, so that is essentially what we see here. And then when we look at the internal force, again, the internal force is just the stress times the area, and the area is a constant in this case. We see very similar behavior, just different units towards what we see with this stress field. Okay, so that's the solution that we get out. So what we have to ask ourselves is, okay, so how does the strain energy in the structure relate? So is this structure seeing similar strains energies as to what the real life, what the exact solution would have seen, or was that quite different? So the question we're asking ourselves is sort of, if we were to plot the stress over the strain, and we think about that sort of that integral over the volume, how those two would relate to each other. So that's essentially what we wanted to get an idea of. Okay, so let's see what we have. So first off, let me see what the time is. I'm going to stop this. It's 30 minutes. I'm going to stop this, and then we work with the